1-fluorobutane. Okay, so remember, this does not matter. This C comes before F. All right? And I've got C4, H, 1, 2, 3, 4, 5, 6, H6, Cl3, Cl3F, and that's how I name that. Okay, so condensed structural diagram would look like this. Okay, that's your condensed structural diagram. Line structural diagram looks like this. 1, 2, 3, 4. And there's a chlorine on carbon 1. There's also a fluorine on carbon 1. Chlorine on carbon 3 and a chlorine on carbon 4. And then I'm done. It doesn't matter which side I put the chlorine on. And then Lewis dot. Let's do these first, all the carbons. Then I have a chlorine, but the chlorine actually has 8 electrons, right? So I need to make sure I fill that. I don't need to do that with the hydrogen because it only has 2 valence electrons to complete an orbit. But all the halogens have 8, so I need to make sure that I include that. And then you add your extra hydrogens. I'm not going to finish this, but add your extra hydrogens and the chlorines with that format that I just gave you. Okay, and that's how you name halogenated hydrocarbons. Okay. So here's a few more, right? So this is ethylene. Ethylene is the main base molecule that or ethene. Ethene is how we make plastics. So your plastics are ethene with halogens added to them, and that makes them really, really stable. Right? And so ethane, right? So you can see here, 1, 2, so dibromo, ethane. Okay, so there's instructions in your notes to show you how to name these. So other halogenated hydrocarbons. So this is DDT, right? And you would know DDT as a pesticide. Okay, it looks like estrogen. So it looks like a female hormone that comes from the endocrine system. So these are called endocrine disruptors, and a lot of our halogenated hydrocarbons are that. So DDT, toxaphene, polychloral biphenyls, right, PCBs. Dioxin is Agent Orange. Agent Orange was used to defoliate the forests in Vietnam during the Vietnam War, right? Lots of children have had dioxin poisoning. Since furans are used for leather tanning, and they're a very volatile chemical that ends up in waterways in developing countries that make leather for us and things like that. So halogenated hydrocarbons are very, very stable molecules. So they basically don't ever break down once they get into a natural ecosystem. And this is a big problem in the oceans right now with plastics, right? So plastics break down into their base components called nurdles, and then they look like fish eggs. Okay, so we have no easy way to get rid of these right now. And that is the big problem with plastics. It comes from, the modification of fossil fuels. So, humans have to make some big decisions about what we're going to do with fossil fuels going forward into the future, because we don't have very effective ways to clean them up. And, obviously they're complicating human-induced climate change as well. So halogenated hydrocarbons, right? And I've already talked about biomagnification, but they will also move up a food chain, right? So remember, they don't break down. And because energy is lost at each level based on the rule of 10, right? Only 10% of the energy storage gets transferred to the next level. You have less biomass at each level, but the same concentration or the same amount of a persistent organic pollutant, right, or a halogenated hydrocarbon. So it might not be a big deal here, but once you get up here, it is a big deal because you have the same amount spread amongst way less organisms. So this is why DDT was a big deal with birds of prey, because the things they ate were consuming DDT in the environment, right? and they were concentrating in the fat tissues. Right, the DDT was concentrating in the fat tissues of birds of prey, and what it was doing was causing the eggs to thin. Right when they laid eggs, so they would break. So the eggs would break when parents sat on their eggs to incubate them, and that almost caused the extinction of things like peregrine falcons. So we've removed DDT from the natural environment, and they're now making a rebound. Okay. So, alcohols is the next functional group that we're going to look at. So, hydrocarbons that have hydroxides attached to them are alcohols. So, the R stands for the carbon chain, or the functional group, and then the OH is what's attached to the carbon chain. So, one carbon with an OH. Now, what we do with hydrocarbons that have OHs, so this would normally be called methane, right? If I didn't have the OH, this would be methane. But what we do is we drop the A and E and add OL, right? So, or OL. So this is called methanol. And you can see that in your data booklet. Alcohol, ethanol, okay? So we name alcohols the same way you would name any of the other molecules, but to designate it as an alcohol, when you have that hydroxide group, you add the OL. Okay. So what do we use them for? Right, a lot of us use E85 ethanol, right? So, so we use it for fuel. It helps engines burn cleaner. So there's strong solvents, disinfectants, fuels, pharmaceuticals, beverages, right? So we use alcohols for a lot of different things. Methanol is mouthwash. Ethanol is the type of alcohol that we drink. Propanol is rubbing alcohol. Okay, so naming alcohols, same thing. Find the functional group on the molecules and circle it. Name the parent chain of atoms, all right? You're going to name carbon 1 closest to the functional group. Okay, and this is how we name, all right? So propan, right? 1, 2, 3 carbons, so propane, but it's a hydroxide. Hydroxide's on carbon 2, so propan 2-all. 1, 2, 3, 4 carbons. This is carbon 1 because it's closest to the hydroxide group. Butan 2-all. Okay, so you can see that as well, right? With side branches, you can have a methyl group attached, right? Methyl group here, 2 methyl, butan 2-all. So the 2 indicates where the hydroxide is, right? So if I give you another example here, so let's look at this one. Okay, so that's in your book. So 3 carbons, so it's propane, but because of the hydroxide, it's propanol, and the OH is on the first carbon, so it's propan 1-all. Propan 1-all. Okay, now this is C3. H, 1, 2, 3, 4, 5, 6, 7. I would say C7, sorry, H7, OH. That's how I would name that. Okay, you could say C3H8O2. That's fine as well. So condensed structural diagram would look like this: CH3, CH2, CH2, CH2OH. Okay, line structural diagram looks like this. OH attached. All right. And then Lewis dot, I'm not going to fill that in. You guys can fill that in on your own. Follow the same structure as the other ones, though. Look at the Lewis dots and then make sure that the bonding structures are correct. Okay, here's another one. let's do this one on the board. 2,2-dimethyl-hexane-3-ol. So I'm going to do this whole thing up to the line structural diagram. So let's put that on the board. Okay, so that is 2,2, then this is on your sheet, 2,2-dimethyl. Hexanol, hexane 3-ol. So it's an alcohol with 6 carbons. That's what the hex stands for. So I'm going to make my parent chain. Okay, so there's my parent chain right there. 6 carbons, and I know that the alcohol is on carbon 3. So let's name these carbons. So let's see, this is the complete structural diagram. Carbon 3, and I've got methyl groups on carbon 2. All right, and then we fill in the rest. So I've got all right. There's my complete structural diagram. So my chemical formula is 1, 2, 3, 4, 5, 6, 7, 8 carbons. C8. And then how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's H17, and I'm going to say OH. Okay, condensed structural diagram is going to be this. CH3, CH2, CH3, CH3, CH, OH, CH2, CH2, CH3. Okay, line structural diagram is 1, 2, 3, 4, 5, 6. On carbon 3 is OH, and then methyl groups. Okay, and I'll let you fill in the rest with that. Okay, so that's 2,2-dimethyl hexane 3-ol. Okay, and that's how we deal with alcohols. The next functional group that you're going to look at is carboxylic acids. And carboxylic acids have a carboxyl functional group. So they have this double bond OOH, and it's always going to be on the end of a carbon chain, okay? So we use carboxylic acids all the time for lots of different things. I'm going to give you a couple examples of what we use them for. Okay, so double bond OOH. Now what we do with these is, we name them the same way as alcohols. Rather than having an ANE or ENE or anything like that, we drop the suffix and add oic acid. So however many hydrocarbons there are, however big the hydrocarbon chain is, you name it that number, right? And then you add oic acid. Okay, so what do we use carboxylic acids for? They make acids in the water, so they have the pH lower than 7, but they are organic acids, so they're not very strong acids. So they don't make as much hydronium. We use them for flavoring, cleaning, soaps, pharmaceuticals, dyes. That's vinegar, right? So acetic acid or ethanoic acid is vinegar. Butanoic acid, right? So stomach acid combined with food makes butanoic acid, and that gives you the scent of vomit. Okay, so same general rules for hydrocarbon naming. So let's give you a few examples here. So pentanoic acid. Okay, so pentanoic acid looks like this. So I'm going to draw the line structural diagram right on the sheet here. So pentanoic acid, I'm going to draw 1, 2, 3, 4, 5. Okay. So 5 carbons, oic acid. And so what happens is on the end, I just add my functional groups and then I'm done. Okay. So let's draw a complete structural diagram for that. So that's my complete structural diagram for pentanoic acid. Condensed structural diagram looks like this. CH3, CH2, 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 and then it's going to be COOH. Okay, or I could expand the double bond OH out on here if I wanted to, but that's how I would name that. Okay, chemical formula is going to be 1, 2, 3, 4, 5. C5. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. H9. H9, and then I'm going to do this. OOH. I can do that, or I can do this. C5H. Oops. C5H10O2. I can do either or. Okay. Now, just like, so this is the next one, just like any of the other functional groups, you could have side branches off of this as well. So this is carbon 1 because it's closest to where the functional group is. So my parent chain is 1, 2, 3, 4 carbons. So it's bute. So it's butane, and it's a carboxylic acid. So it's butanoic acid. Butanoic acid. And there's a methyl group. So it's 3-methyl butanoic acid. Okay, 3-methyl butanoic acid. And that's going to be, it's actually the same chemical formula. C5H10O2. All right, I'm not going to do the complete structural diagram, but the line structural looks like that. Okay, and that's how we name carboxylic acids. All right. Okay, so I'm gonna end this lesson here right now because I'm gonna run out of time on my camera, but I'm gonna continue. I talk about esters. I'm gonna finish up this lecture with my next video. Okay, and then I'm gonna give you I'll give you guys an outline for what types of assignments that I want you to do. Okay, so that'll be it for this lecture. We will talk to you in a little bit.